In this second tutorial, we will find compositions of functions and state the domain. So at this level, when we're talking about domain, really we're only talking about whenever there's a denominator. We already talked about this in the previous tutorial. If we divide two functions together, if we have a denominator, our denominators can never be equal to 0. So we do have to watch out for domain when we're talking about division. If we're just multiplying functions or adding or subtracting and there's no denominators involved, then our domain will be all real numbers. But if there is a denominator, we have to watch out. We might have to restrict a few numbers from our domain. So let's look at composition and then talk about domain. So here's composition. Given two functions, let's call them f of x and g of x, the composite function has this symbol, f of g of x. And what this is, if you want to read what this says, it means f of g of x. That's how you read this symbol, f of g of x. And I sort of think of this as like a big box that has a smaller box inside of it, f of x being the bigger box and g of x being the tinier box. Or if you know what nested eggs are, you open up one of the eggs and then there's a smaller egg inside, and then you open up the smaller egg and there's an even smaller egg inside that one, and so on and so forth. You always start from the inside and deal with that function, and then you do the bigger function of that function. So instead of going back and looking at one of the previous examples, instead of looking at f of a and just plugging in an a, you're looking at something like g of an entire function. You're picking up an entire binomial, for example, and putting it into another function. That's what composite functions are. If we're talking about the domain of a composition is the set of all the x values that satisfy g of x, the smaller function, if you will, the one inside the bigger parentheses. Make sure that x satisfies g of x. And then you also have to make sure that then the g of x values are in the domain of your bigger function. Really, we just have to watch out for denominators. It's not going to be too bad. Here's a new set of functions. Here's another 7. They're different functions. And let's start with compositions involving numbers. I think that that's an easier input to deal with. Let's say we have this one, and this is how you would read it. A of d of 5. Basically, we're going to start inside with d of 5. I'm going to start with that function. Find d of 5 for me. Okay, that's not too bad. I'm going to go to the d function, and here it is. And instead of having an x, we're going to replace that x with a 5. So d of 5, instead of x minus 2, it's 5 minus 2. So d of 5, of course, is 3. And now I'm not finished. This is just halfway. Once I know what d of 5 is, I can kind of cancel that out and put that 3 in its place. So I ultimately want to know what a of d of 5 is. Well, if d of 5 is 3, then really I'm looking for a of 3. And that's what I'm going to do now. That means I'm looking for a of 3. Obviously dealing with a different function and a different input. So here's a of x. It says 3x minus 2. A of 3 will be 3 3's minus 2. So 3 times 3, I'm going to put it in parentheses, minus 2. That, of course, is 9 minus 2, and that is 7. So a of d of 5 equals 7. Notice that's the only thing I boxed or circled. I might underline the middle number that I find. I'm looking for a of d of 5. I find d of 5 first, and then plug that back in and find a of that number, and I have my final answer. Let's see if we can do that again with maybe two different functions and some different numbers. G of e of 9. Let's first start with e of 9. Let's figure out what e of 9 is. Where is e of x? And that is, oh, here it is. E of x is the square root of x. So e of 9 is the square root of 9. Just replace the x with a 9. And that, of course, is, yeah, that's weird. It's 3 again. That's okay. It's not always going to be 3 as that first number. Once we know what that first function becomes, then I'm going to plug that right back in, and I'm going to, let me change colors here, And then I'm going to deal with g of that number. So 3 will take the place of e of 9. So g of 3. And now let's see what g of 3 is. That's over here. So I've got x squared minus 2x plus 1. Each of those places where there's an input, I'm going to put a 3 in place. So 3 squared minus 2 3's plus 1. Look at it again. Input squared, here's input squared. Minus 2 inputs, here's minus 2 inputs. Plus 1, plus 1. And let's see what that is. That equals 9 minus 6 plus 1. That equals 3 plus 1. That equals 4. Awesome. You don't always have to deal with two functions. How about this one? B of B of B of 2. Oh my goodness. That's fine. Just work inside out. I'm going to start with the very innermost b of 2. And let's see what that is. So b of 2. Let's see what the b of x function is. It just says x squared. That's cool. I'm going to take my input and I'm going to square it. So b of 2 becomes 2 squared, which is 4. So that's, I would say, half the way, but in this case it's 1/3 of the way. So that b of 2 is gone. And now I'm going to put that 4 into, well, the b function again. And let's see what we've got. So now we're talking about b of 4. Well, obviously that's going to be equal to 4 squared, which is 16. Usually we'd be done, but we're dealing with 3 functions, or actually the same function, but 3 times. So now 16 is going to go back into this one, because now we're finished with that. And finally, we're going to do our last one, which is b of 16, which would be 16 squared, which would be 256. So b of b of b of 2 is not really much more difficult than g of e of 9. We're just dealing with the same function 3 different times. Follow my work, follow the arrows, follow the colors perhaps, and that's composition. At least that's composition with numbers. Let's throw some variables into it now. Same functions, and now let's deal with a of b of x. We did a of b of some number, but now let's do a of b of x. That's okay. B of x is where we're going to start. We're going to start with this function, b of x, which we actually know what b of x is. It's right here. It's x squared. So b of x is x squared. So ultimately this is going to go away, and the x squared is going to take its place. It's not a number this time. It's just an expression, a whole other function. So we're not dealing with a of b of x anymore. We're dealing with a of x squared. A of x squared says take the a function and input x squared. Everywhere you see an x in the a function, put an x squared. So I see the a function is 3x minus 2. So a of x squared is going to be 3x squared minus 2. And that's actually it. There's nothing more to do. There's no like terms. There's nothing more to do. So I'm going to box that in, and I'm finished. So when you're dealing with variables, your answer is going to, have the variables in the end. If you're dealing with numbers, well, your answer is going to be a number in the end. Let's look at b of a of x. If we can do a of b of x, we should be able to do b of a of x. Now, some people might say, well, maybe they're just the same thing. That is very rarely the case because we are dealing with 2 different functions and we're dealing with 2 different compositions. A of b is different than b of a, most likely. But it's the same idea. We're going to start with a of x. We're going to start with the inside function. A of x is this 3x minus 2. Okay, and then we're going to take that function and replace it in here, kind of scratch this out and put b of that function, b of 3x minus 2. Well, b of x says take the x and square it. So b of 3x minus 2 will say take the 3x minus 2 and square it. This is another nice example because we're trying to square a binomial. Squaring a binomial is writing the binomial side by side and foiling. Our first terms give us 9x squared. Some of you can just jump into the inner terms, and the outer terms will always be the same when you're squaring a binomial. So if one of them is negative 6x, the other is negative 6x, which is why they always double, in this case to negative 12x. And then my last terms are plus 4. If you want to show a middle step there and then combine your like terms, that's absolutely fine as well. But that's that composition, b of a of x. And clearly, these are not the same things. They are not the same thing. So a of b of x is not the same thing as b of a of x. How about e of f of x? Two different functions. Let's start with f of x. F of x is right here, 4x plus 9. So we're going to take that function and we're going to put it right back in here into the e function. So let's see what we have here. I'm going to try to draw my arrows over to here. Okay, so we have e of 4x plus 9. And I'm going to write it underneath here. I'll put my equal sign here. E, let's see, where's e? That's that square root function. So the square root of something. Well, this time my something is this 4x plus 9. So it's just the square root of 4x plus 9. Now, there's nothing more to do. We would want to simplify this if we could, but we cannot. I understand that the square root of 4 is 2 and that the square root of 9 is 3, but the square root of 4x plus 9 is nothing. It's not a perfect square because the plus sign makes these two terms have to go together, and it's not all a perfect square. So that's all that we can do. We can't simplify that anymore. All right, so that was kind of an easy one. And then c of d of x. Let's start with d of x. D of x is right here, x minus 2. So d of x, x minus 2. And we're going to plug that right in here into the c function. Change color. And I will have c of x minus 2. Again, I've run out of room here, so I'll just put it underneath here. That's fine. C of x minus 2. So this is 3x to the negative 1. Actually, I believe on your note sheet, I changed this from what it looks like here and changed that x to the negative 1. A negative exponent just means that it's divided by x. So the 3 is up top and the x is down in the denominator. These, of course, mean the same thing, but I think on the note sheet I typed it like this. Okay, so that's fine. So c of x is 3 divided by an input. And in this case, if my input is x minus 2, then it would be 3 divided by x minus 2. And that's our composition. Now let's talk about domain, and that's the last thing we need to do. I want to state the domain for number 13, which is right here, and for number 16, which is right here. Let's talk about number 13. Remember, the only thing we have to watch out for right now is denominators. So if we're looking for a of b of x, we need to first talk about b of x, that function. So let's look at that function. Here it is, x squared, or here it is, x squared. I don't see any denominators, so I don't see any restrictions. I could plug anything I want in here for x. So all real numbers is the domain for b of x. But then we're going to plug it into a of x, and a of x is right here. Well, but there's still no denominator, so we don't have to worry about that. I don't see a denominator at all anywhere in this thing, in this problem. So the domain is going to be the set of all real numbers. And you could say that like that, or you can say that negative infinity to positive infinity. X can be anything in this example. No denominators. In fact, the only denominator I see on the page is all the way over here. So if I'm looking for the domain of c of d of x, first talk about d of x, and here it is, x minus 2. Well, there's no problem with that. I can plug anything I want in for here for x. There's no denominators. So that's okay. Except that I'm about to plug that into the c. And the c of x makes my function 3 over x minus 2. And now I have a denominator. Denominators can never be equal to 0. We can never divide by 0. So the domain here is going to be all x except for 2. Because if x were 2, then 2 minus 2 is no good. 2 minus 2 is no good, so x is not equal to 2. We cannot divide by 0, so we have to rule out 2. Now I choose to use set notation. If you want to use interval notation, I'll just put an or. You could say negative infinity to 2 and then union that with 2 to infinity. I feel like that's a little bit more writing, but if that makes more sense to you, then please by all means use interval notation. I choose to use set notation because it's just one little number that x cannot be, and there it is. So that's composition. Go back and watch this tutorial or any part if you need to, and watch out for domain, which is just look out for denominators and make sure that numbers will not make 0 in the denominator. We'll practice this more in class, and I'll see you then. Thanks for watching.